Have you ever, like, I don't know, wished you could just, like, download knowledge straight into your brain?
Yeah.
Like, when you're faced with something incredibly complex,
Yeah.
say, I don't know, artificial general intelligence or AGI, it's like you just want the core ideas, right? Without having to wade through tons and tons of research papers and articles.
Yeah, definitely.
Well, that's exactly what we're doing today on the deep dive.
Yeah.
We're taking this amazing set of sources that you shared with us,
Right.
and we're going to unpack what AGI actually is, and even more exciting, how we might actually get there.
Yeah, I'm really excited about this one. We're diving deep into the fundamental definitions, the current hurdles we're facing in AI,
Uh-huh.
and some of the most, well, honestly, some of the wildest paths people are proposing to reach this super ambitious goal.
I love it. It's like, think of this as your carefully curated shortcut to
Exactly.
actually grasping the essentials of AGI.
Yeah.
Our mission today is to give you a much clearer picture of this field because it's changing so rapidly. And it's so easy to get lost in all the buzzwords and the hype.
Oh, absolutely.
We're going to cut through all that and zero in on the core concepts
Yeah.
and the real challenges that are facing AGI. We want you to walk away from this deep dive feeling like, okay, I actually get it now,
Right.
without feeling totally overwhelmed.
Exactly. Informed, but not overloaded.
Precisely.
So to kick things off, I think we should tackle this fundamental question. What does intelligence actually even mean? Whether we're talking about humans or machines, it's not as straightforward as it seems, is it?
It's deceptively simple, that question. And, some of the early sources that you sent over, I think it was John 92 and LB 91, highlighted how a lot of our understanding of intelligence is kind of filtered through a human-centric lens.
Mhm.
We tend to judge other systems, whether it's animals or AI, based on how we think.
It's true. It's this inherent bias we have.
Yeah.
And that immediately brings up a challenge, right?
Mhm.
How do you come up with a definition of intelligence that's broad enough
Yeah.
to actually encompass all sorts of entities? Like the tests that we use to gauge intelligence in humans, those wouldn't really apply to, a super sophisticated
Yeah.
chatbot
Right.
or even a really different biological organism.
Yeah.
So instead of just focusing on specific human-like traits, maybe we need to think about the more fundamental aspects, the
Yeah.
things that could underlie intelligence
Yeah.
in any system.
It's like, I don't know, trying to define communication by only studying human language.
Yeah.
You'd miss out on all the other ways that information can be exchanged, like even between, trees in a forest or something like that.
Absolutely. You'd miss the whole picture.
And speaking of human intelligence, our sources also touched upon IQ tests. NBB plus 96 and GOT 97B come to mind. It's amazing how much debate there is about what these tests actually capture. Like, they're statistically consistent for humans, they can predict certain things, but is that the full picture of what intelligence really is?
That's the core of the debate, isn't it?
Yeah.
Some people argue that IQ tests, they do tap into this fundamental aspect of cognitive ability, while others say, no, they're just measuring this very specific set of skills.
Right.
And the American Psychological Association actually offered a pretty interesting, it was a pretty comprehensive definition of intelligence in MBB plus 96. They described it as the ability to understand complex ideas, adapt to the environment, learn from experience, and reason effectively.
Okay.
And also to overcome obstacles through thought.
That's a mouthful.
It is.
But it does seem pretty encompassing.
It does.
And back in 37, Bingham, he offered this really concise thought. He said, intelligence is simply the ability to solve new problems, bin 37.
And then Wechsler, he added this important element of purposeful action, rational thinking, and being effective in your environment. Wex 58. It seems like these different definitions are kind of circling around this idea of being effective and adaptable, whatever context you're in.
They are, like being able to navigate and thrive in your environment,
Yeah.
whatever that environment might be. And one of our sources, Legg and Hutter, they offered a more abstract perspective. They suggested that intelligence isn't about possessing a specific set of abilities.
Okay.
It's more about the outcome of those abilities. What's really interesting is this idea that intelligence could even emerge from capacities that humans don't have.
Ooh, that's a mind bender.
It is, and that really broadens our thinking about what machine intelligence could look like.
It does. Okay, so we've wrestled with this idea of defining intelligence in a general sense. Now let's bring it back to the world of machines. Let's talk about machine intelligence.
And specifically artificial general intelligence. One of the papers, Hutter, talks about this idea of an agent that's interacting with an environment, and it gets these rewards for achieving certain goals. That sounds like a pretty fundamental way to think about AI, wouldn't you say?
Yeah, it really is. This idea of an agent and an environment and learning through rewards, it's central to this whole area of AI called reinforcement learning.
Right.
And the key here is for an agent to get those rewards, it needs to learn about the structure of its environment, like what actions lead to the outcomes that it wants. This really highlights how important learning is as a basic parts of intelligence, really.
And this brings us to AGI, right?
Yeah.
Our sources describe it as this system that can perform a wide range of tasks
Right.
without needing to be specifically programmed for each one.
Yeah.
Kind of like human general intelligence, HGI, Kanaya and Magin, Gertzel and Penichin, 2006. And it's interesting, one of the papers, Kanaya and Magin, points out that AGI, it used to be seen as this really, really distant goal until pretty recently with all these advancements in these large language models.
That's right. The things these LLMs are doing now, it's really brought AGI back into the conversation.
It has.
The fundamental goal of AGI is to achieve human-level intellectual capabilities across a huge range of problems, Doc. And then there's this term, HCAGI,
Okay.
Human-Capable AGI.
Oh.
And that refers to AI systems that could perform all the intellectually demanding tasks that humans can, and maybe even surpass us in some areas, Ringel Morris et al.
Which is, well, kind of a mind-blowing thought, if you really think about it.
Yes, yeah.
But just to be clear, AGI, even HTAGI, is fundamentally different from the narrow AI that we see all around us today, right?
Oh, yeah, absolutely.
Like narrow AI can do amazing things like play Go or recognize faces in a photo,
Right.
but it can't suddenly switch gears and start writing a research paper or composing a symphony. It lacks that ability to generalize, to adapt to new things. Ringel Morris et al., Doc.
Right, it's specialized. Like your voice assistant can set timers and play music, but it can't, suddenly start debating philosophy with you. That lack of this broad, adaptable intelligence, that's the key difference between narrow AI and AGI. AGI is this promise, this challenge of something much bigger.
Okay, so we've got a better understanding of what AGI is. Now comes the really juicy part. If we want to build it, what are the biggest hurdles standing in our way? What are the limitations of current AI that we need to overcome? One thing that jumped out from our sources is this idea that even when current AI does achieve something, it might be doing it in a way that's totally different from how a human would Kanaya and imagine Hernandez Oralo 2017a.
That's such an important point. It's about the underlying methodology. Current AI, it often leverages these massive advantages that it has, like huge data storage, incredible computational power, processing speed. It tackles problems through sheer brute force in a way that humans just can't. Think of like a chess AI that analyzes millions of potential moves in a second. That's not how human intuition works, not how human strategic thinking works.
Right. It's like comparing, a supercomputer doing complex calculations to a human using a pen and paper.
Yeah, yeah.
They might both get to the same answer, but the process, the underlying understanding is total different.
Totally different approaches.
And this brings us to these large language models, or LLMs,
Yeah.
which have been so dominant in the AI field recently. One key limitation that was pointed out is that they're mainly trained on this thing called next token prediction. Kanaya and Magin, Phelan Hawley August 2024, SSRN6. Which sounds pretty technical. So what does that actually mean for their intelligence?
Well, basically, it means that LLMs are incredibly good at predicting what the next word in the sequence is going to be based on the massive amounts of text they've been trained on. Their outputs are based on these statistical patterns and associations that they've learned from all that data. And that's why they can generate text that sounds so fluent and coherent. But the flip side is, it also means they might struggle with creating truly new knowledge or forming beliefs about the future that go beyond just extrapolating from the patterns they've already seen. Phil and August 2024, SSRN6. Think of it like your phone suggesting the next word as you type. LLMs are doing something similar, but on a much grander scale.
So they're really good at mimicking, at remixing information that already exists, but maybe not so great at genuine originality or understanding cause and effect in the same way that humans do. One of the sources used this great phrase. It called it superhuman banality, Ringel Morris et al. And they even gave an example of, I think it was ChatGPT writing a poem. It was technically impressive, but it just lacked that spark, that deeper meaning that you find in human poetry. Sadly.
Exactly. They can produce outputs that seem impressive on the surface, but often lack that genuine depth, that real understanding. And it's not just about the quality of the output either. There are also more fundamental computational limitations. One paper, Han Ha20 cited in Rail Morris et al., pointed out that these self-attention mechanisms, which are like a core part of how LLMs work, they can struggle to understand hierarchical structures in formal languages unless you keep adding more and more layers or attention heads.
Yeah.
And those structures are crucial in human language and logical reasoning.
So it's like just making these models bigger and training them on more data might not be enough
Right.
to overcome some of these inherent limitations. Our sources also mention limitations in areas like theory of mind,
Right.
understanding that other people have their own thoughts and beliefs and intentions separate from your own,
Yeah.
and even a sense of self-understanding. Ringel Morris et al., SLFC 22 cited therein. These seem like pretty crucial aspects of general intelligence.
They do. And those are really complex cognitive abilities. They seem to go beyond just predicting the next word in a sequence, right?
Yeah.
One paper actually gave a specific example, a math problem that even advanced models like GPT-4 struggled with. Ringel Morris et al., Bright 23, cited therein. It was about finding an integer with a specific prime-related property. And it showed that even with all this knowledge, applying logical reasoning in new or slightly unusual ways can still be really tough for these models.
That's a great example. It really shows that, just having access to tons of information, it doesn't automatically equal the ability to reason effectively. And it's not just about abstract reasoning either.
Right.
One of the newer papers we looked at, Shang et al., it talked about these reasoning in a haystack experiments. And they showed that LLMs, they can struggle to retrieve relevant information and to reason within really long pieces of text. So it seems like their effective context window, that's like the amount of text they can really understand at once, might be smaller than we think.
Yeah, that's a big practical limitation.
Mm.
This idea that we can just keep feeding LLMs longer and longer documents and they'll flawlessly process it, it seems to have its limits. And this also reinforces the point that just scaling up these LLMs with larger context windows, it might not be the ultimate answer.
Right.
There might be some fundamental reasoning limitations that need a totally different approach.
And on top of that, there are the very real practical limitations, right?
Oh, absolutely.
Our sources mention the huge cost of computing power and energy consumption just to train and run these giant models. Ringel Morris et al. That makes development much more challenging, and it also raises environmental concerns.
Yeah, the ecological impact is a big consideration.
Yeah.
So it's not just about whether we can build it, but also can we build it sustainably in a way that's accessible to everyone?
Okay, so we've taken a good look at what AGI is and some of the key limitations that are holding us back, especially when it comes to LLMs. Now let's shift gears and talk solutions. What are some of the potential pathways, the different approaches that researchers are looking at to actually achieve AGI? One idea that came up was this patternist philosophy of mind, Goertzel. Can you tell us more about that?
Sure. This perspective, it's really connected to Ben Goertzel's work. It basically sees intelligence as being fundamentally about understanding and creating patterns. It's not just about recognizing patterns that are already in the data, but also the ability of the system to create new patterns. And then to organize those patterns in these complex interconnected ways, like hierarchical and heterarchical networks. There's also this idea of a dual network, where different types of pattern organization are working together. So the key is the dynamic creation and organization of patterns, not just storing knowledge statically.
So it's not just passively absorbing what's already there, but actually actively building new relationships and information. That's a pretty interesting shift in thinking.
Yeah, it is.
And this seems to connect to another idea, combinatory function optimization, or COFO Goertzel. What's the basic idea behind that?
So imagine systems that are designed to find the best solution to a problem by trying out different combinations of things. It's like you have this function you want to maximize, which could be like achieving a specific goal. And you use a guided process to select and combine different components to get closer and closer to that maximum. The idea is this kind of optimization through combinations. It could be a fundamental building block for how we architect AGI.
The source even mentions some pretty technical terms like Galois connections and chronomorphisms as ways to implement this Goertzel. We don't have to go deep into the math, but what's the general significance of these concepts?
Right, you don't need to get lost in the weeds there. Essentially, these are advanced math tools that give us a framework for building QFO systems in software. They help in designing systems that can effectively explore and optimize combinations. The main takeaway is the mathematical properties of those combinatory operations, especially associativity, are really important for being able to represent knowledge hierarchically and for making QFO dynamics work efficiently.
So it sounds like a very structured, almost algorithmic approach to building intelligence. Now, there's another idea pretty different from that, the concept of universal intelligence, Hutter, Legg, and Hutter. This seemed to take a really abstract, almost mathematical way of defining intelligence.
It does. Universal intelligence, often represented by the Greek letter or, is this theoretical measure of how well an agent can achieve its goals across a huge, practically infinite range of possible environments. The equation that describes it involves the agent, the environment, a value function that shows how successful the agent is in that environment, and crucially, the Kolmogorov complexity of the environment.
Kolmogorov complexity. If I remember correctly, that's basically the shortest computer program you could write that would completely describe something, right? So simpler environments would have lower Kolmogorov complexity.
Exactly. And the equation for universal intelligence, it weights the agent's performance in each environment based on its complexity. So how well it does in simpler environments contributes more significantly to its overall measure of intelligence. It's like a mathematical way of saying simpler explanations, or in this case, better performance in simpler environments, are preferred. So an agent with high universal intelligence, it would be expected to do well in all sorts of environments, both simple and complex.
That makes sense. But the paper also mentioned that Kolmogorov complexity is uncomputable, which seems like a pretty big problem if you want to actually use this to measure or build intelligence.
It is. In its purest form, universal intelligence is more of a theoretical framework. It's a way to understand what general intelligence is at its core. It's not really a practical blueprint for building an AGI, but the thought is maybe we can approximate it by testing an agent in a bunch of randomly generated environments or by trying to classify environments based on how complex they are.
Ugh.
But as the paper itself says, there are some pretty significant practical challenges in doing this in a truly comprehensive way.
So more of a guiding principle than a step-by-step guide. Switching gears back to something that's maybe a bit more directly applicable, one of our sources talked about this idea of building an intelligent world as a way to get to AGI, Joshi, Sheng et al. What's the core idea behind that?
So the idea here is instead of just focusing on what's inside the intelligent machine, we should also focus on creating an environment that closely resembles our own world. It could be a simulation or a really advanced augmented reality. The argument is that, for humans, a lot of our intelligence and reasoning is tied to our experience in the world, our understanding of how things work around us. And pre-trained embeddings, which are basically these numerical representations of concepts and their relationships, they can play a big role in grounding AI in this kind of world.
So it's like these embeddings can help the AI understand things like physical relationships, common sense knowledge, maybe even some of our implicit unspoken understanding of the world,
Exactly.
just by being immersed in this simulated environment. And this idea of continuous learning, that comes from the AI constantly interacting with and learning from this world-like context, right?
Exactly. Proponents of this view argue that by putting reasoning within this complex, realistic environment, we might be able to bridge that gap towards human-like general intelligence. The world itself becomes a source of constant information and learning opportunities.
Now, another very intuitive approach is this idea of brain-inspired AGI aspects, S4159802592197. I mean, after all, the human brain is the best example of general intelligence we have.
It's true. The logic is, if we can copy the structure and function of the brain, maybe we can replicate that emergent intelligence. This means using artificial neural networks, which are kind of loosely based on the brain's architecture of neurons and connections. And there's also a lot of interest in developing this thing called neuromorphic hardware,
Okay.
which are basically specialized computer chips designed to be more like the brain's neural circuitry, more direct and also more energy efficient.
And what about that idea of layered processing in neural networks,
Right.
where different layers handle different levels of abstraction, from basic sensory input up to more complex concepts?
Right, that's also inspired by how the brain seems to work. This layered approach lets the system build more and more complex understandings from simpler inputs. And the source even mentioned things like hybrid platforms like the Tianjik chip, which combines different computational approaches, and neuroevolution, which uses evolutionary algorithms to design and optimize the neural network structures automatically.
It's like we're trying to reverse engineer the most successful intelligence system that we know.
We are, in a way.
There were a couple other really distinct approaches highlighted. One was NARS, the non-axiomatic reasoning system Wang, AGI aspects, 67, half 95, ECBate, MANC 724, Phi 057, C879500. it seems to operate on a whole different set of principles.
It does. NARS is this AGI project that's built on the principle of adaptation under knowledge resource restrictions, which they often shorten to AIKR.
Okay.
The core idea is intelligence, whether it's biological or artificial, needs to be able to function even when it has limited information and computational resources.
Which is certainly true for humans in most real-world situations.
Exactly. At the heart of NARS is non-axiomatic logic, or NAL.
Okay.
It's designed to handle uncertainty, to work with limited evidence. It uses truth values that are based on experience rather than absolute certainty. And it uses this memory structure that's organized around concepts and how they relate to each other.
So it's not about having huge amounts of perfect data. It's about being able to reason and make decisions with incomplete or uncertain information.
Right. It's about dealing with the messiness of the real world.
Yeah.
And one of our more recent sources, Hammer, Wang, brought up this idea of machine psychology and how it's connected to NARS and this concept of operant conditioning. That was a really interesting intersection of ideas.
It was.
So machine psychology tries to take principles from learning psychology, especially operant conditioning, the idea that we learn through rewards and punishments. And they try to integrate that with the theoretical framework and implementation of NARS. They use the sensoromotor version of OpenRs for Applications, or ONA, as a platform to explore how these principles can help build intelligent systems that can learn and adapt through interacting with their environment, driven by the reasoning capabilities of ONA.
So it's about building a system that not only reasons, but also learns from its experiences, its successes and failures, in a meaningful way.
Exactly. Kind of like how animals learn.
The source even briefly described this working cycle of NARS, this probabilistic selection of concepts and tasks and beliefs from memory, and then using inference to derive new knowledge or make decisions. 67 UNI5Ns AP9CI724 FO7T87C795A0. It's like a continuous loop of exploration, reasoning, and learning.
Right. It's a dynamic process where the system is always choosing what to focus on, what to believe based on what it knows, and then using that information to generate new inferences or solve tasks. There's another interesting idea that came from one of our newer papers, Shang et al., called AI native memory. This proposes a different way to think about how memory could work with LLMs and future AI systems.
It's not just about giving LLMs bigger databases, right? It's about designing memory systems that can actually store the conclusions and insights that are derived from reasoning processes directly within the memory itself.
Right, so the system can easily access and connect related information and maybe even simplify complex inferences later on.
Instead of just pulling up raw text or data, the system would be able to access previously reasoned conclusions.
Exactly. The more ambiguous vision is to have these personal, lifelong AI-native models, maybe super deep neural networks, that can basically compress and store all types of memories, even those that are hard to express in language. It's about building a more integrated, more reasoning-aware kind of memory.
That sounds incredibly powerful. One last thought that really stood out. One of our sources, Phelan Hall Lake, August 2024 SSRN6, made this compelling argument about the limits of relying so heavily on data-driven prediction. And it emphasized the importance of theory and causal reasoning.
Yeah, that was a great point. It highlights that while AI is great at spotting patterns and making predictions from past data, human intelligence can build theories about how the world works and understand cause and effect. This lets us go beyond just looking at what happened before, to imagine new possibilities, intervene in the world, and create genuinely new knowledge. The example they used, the Wright brothers building a theory of flight even when the data didn't support their ideas, was a great illustration of this uniquely human ability.
It really shows how powerful that ability is to create these abstract models of the world and to test those models, even when the evidence might be limited. It seems like that's a crucial gap for AGI to bridge.
It is. Moving from just sophisticated prediction to true understanding, and to the ability to come up with new theoretical insights. And that brings us to some overarching challenges in the pursuit of AGI. One big one is finding this balance between generality, so the ability to do lots of different things, and the level of performance in each of those things, Ringel Morris et al.
Right. It's not enough to be a jack of all trades if you're a master of none.
Exactly. And then there's the ongoing debate about whether true AGI needs a physical body, like a robot, to interact with the world, or if it can exist just in a cognitive realm focused on thinking and information processing, Ringel Morris et al.
Right now, it seems like a lot of the definitions and research is more focused on those cognitive aspects.
Right. The ability to think, to reason, to learn in a general way is seen as central,
Yeah.
whether or not that intelligence has a physical form. But some of the definitions we discussed earlier suggest that certain tasks, things like adapting to a new environment or solving practical problems, might actually need some form of embodiment.
That's a good point. One of the other interesting points that came up was the importance of metacognition, Ringel Morris et al. Things like being able to learn new skills effectively, knowing when to ask for help, even social metacognition, like theory of mind.
Right.
These abilities to think about your own thinking, they seem like really important benchmarks for achieving true general intelligence.
Absolutely. A truly general intelligence would likely need to understand its own limits, learn new things, and be able to interact effectively with other intelligent agents. And of course, we can't talk about AGI without mentioning the big questions of safety and alignment, Doc. Ringel Morris et al., Muehlhauser, 2013. Making sure AGI is aligned with human values and that we can prevent unintended harm, that's absolutely crucial.
It's a future with huge potential, but also one that demands that we think carefully about potential risks. One source, Shang et al., also proposed this idea that AGI might not be a single thing that we achieve, but rather a continuous process of getting better and better over time.
Yeah, more of an evolution than a revolution.
And this framework for classifying AGI by its performance, its generality, and its autonomy, Ringel Morris et al., that seems like a useful way to measure how much progress we're making.
Definitely. It gives us a more nuanced way to talk about AGI, to see that there will probably be different stages of development rather than just this one moment where we suddenly have general intelligence.
So we've really explored a lot today. We've taken this deep dive into the world of AGI, looking at the challenges in defining intelligence itself, the limitations of our current AI, and all these different approaches that researchers are exploring. It's clear that AGI is a really complex goal with lots of questions still unanswered.
It is. And as we wrap up this deep dive, I want to leave you with a final thought. Given everything we've discussed today, all the different definitions of intelligence, the various paths to AGI, what do you think will be the most crucial breakthrough, the key insight that will get us there? And what happens if we choose one particular approach over the others? Do we need to perfectly mimic human intelligence? Or will some new, maybe even non-human-like form of machine intelligence be the answer?
That's a really thought-provoking question. Definitely something to ponder. And if you want to explore this further, we encourage you to check out the research we've talked about today. This journey to understanding and maybe even creating AGI, it's an ongoing deep dive. We've only just scratched the surface. Thanks for joining us on the deep dive.